is there a better way than random sampling to get an accurate estimation of SN ratio? This is Takuchi's proposal. He proposed a cross-array design of experiment. This is a sampling method by using outer orthogonal array. And as I mentioned here, you see, in the first page, it will tell you that are 3 sources for the noise factors. That was the first question I asked in the last class. First one is external. Second one is internal, which are related to the aging time. When you use the product for a long time, that your property might getting worse, such as fatigue, wear, weather. The third one is from manufacturing. When you manufacture something, there will be tolerance associated with this manufacturing process. Or if you are buying some material, there will be some variation for the material you bought. Therefore, these 3 noise factors will contribute the variation of your output, since your input will have some variation due to these 3 noise. How do we get a good sampling without using a lot of samples? He suggests, as I mentioned here, random sampling. You will require large sampling. So he suggests we should use, since orthogonal array is a very effective method, that we can arrange the factors in a way we'll have a balance and symmetric selections for the samples. So Takuchi proposed, then why not we use orthogonal array, another orthogonal array for the noise factors. By arranging this important noise factor, there will be a lot of noise factor. Right now, we only need to concern about these important noise factors into an orthogonal array. So we can use a small number of experiments, since orthogonal array is a fractional factorial, right? Only a small portion of the full combination. So we can control the number of the samples to make sure there will be only a small number of samples. But this small number of samples will be balanced and symmetric. That how come, I mean, since we are using the orthogonal array, so we can make sure that our sample will be evenly distributed. So will be evenly sampled. Since this is the property of orthogonal array, they will be symmetric and balanced. Or we can use another method called compound noise factors, which will be introduced in the next chapters. So first, we using the similar method to factorize our noise factors. As I mentioned before, the noise factors usually coming from either manufacturing errors or external errors or internal errors. No matter which one, we often using a tolerance range to represent the possible variation for the variable. If it is a manufacturing noise, often to be, for instance, plus and minus 10%. Or say, if it is external noise, like outside temperature, the temperature could be minus, the operating temperature could be minus 20 to 60. This is 2 types of manufacturing error. I mean, 2 types of noise factors. First one is manufacturing error. The second one is external. So how can we make this noise factor to be a factorial factors? If it is a manufacturing errors, we use the tolerance range. Then we can set the upper and lower bound to be, I would suggest you the lower bound using minus, the upper bound using plus. So level 1 minus, level 2 plus. They'll be more consistent, will be more consistent to people's first impression, right? So small in the first level, large in the second level. And If it is external, then we can use the lower bound of the external noise in the first level and the upper bound of the noise factor as the second level. So like the temperature, we can use level 1 to be minus 20 degree, level 2 to be plus 60 degree. If usually we just use 2 levels, sometimes in case you need to use 3 level for the noise factors, in case you worry that this noise factor might be highly nonlinear to the output, then you can use 3 level. If it is 3 level, it is very simple. The first level will be the lower bound. The third level will be the upper bound. But in the second level, we use the middle value, the nominal value, which means that no error. And for the external noise, if it is a range, lower bound in the level 1, upper bound in the level 3, and the middle value or the nominal value will be the level 2 in case you want to use 3 level. Okay, then how do we do? So for a control variables, we put it in an orthogonal array. We call it inner orthogonal array. And again, we put these noise factors in another orthogonal array. We call it outer orthogonal array. And by using this outer orthogonal array, we apply this noise to this one. This we call it design 1. In this inner array, we call design. And we find out what will be the output when this design is subjected to different combination of noise. Therefore, we will have this sample. From this sample, we can get the average standard deviation. Then we can estimate the SN ratio. This is how it works. So we will use this outer array to be the sampling strategy to reduce the number of samples, however, maintain the balance and also symmetric inference for each noise factors. So we call, again, this is inner array for control factor. This is inner array for control factor. And this is outer array, we call it outer array for noise factors. For each combination in the inner array, we call it design. This is different design. For each design, we will do sample. In the past, we are using random sampling, but now we are using outer array to make our output to be a certain, due to certain combination of this noise. In such a way, we will understand what will be the performance of this design when it is under this influence of the noise. So go through each outer array, we'll get this different output. Then we can calculate the mean standard deviation. Therefore, we can have the SN ratio. Continue. Work on the same, using the same strategy for the second sample. For the second sample, then we can continue finish all the samples. All right, so this is the inner and outer orthogonal array design. As I mentioned before, inner array is for control factors. Each treatment stands for different design. Each outer array is for noise and noise factors. Each outer array, each combination in the outer array represent one sampling result. Usually, we will use 2 levels. Since for the noise factors, the range is usually small and the inference on the output are usually monotonic. Usually, we just select 2 levels. As I mentioned before, in case you worry about the nonlinearity of the noise factor, you can use 3 levels. This is the design. 1, go through different sample. Sample 1, sample 2, continue, and you will have SN ratio 1. Next, you will come to design number 2, and working on the same orthogonal array and another sampling. We have another sampling for using outer array. Then we have average, standard deviation, and we'll have the SN ratio. Continue all the way down, finish all the inner array. You have all this SN ratio for all the inner array design. Video tape, we're using this one as an example. I will go through that very quickly, and then we will be using Excel as an example to finish that. This is a cantilever beam, and we want to design the stiffness of this cantilever beam in such a way that the stiffness K will be equal to 1 rand per millimeter diffraction. And the initial design, Young's modulus, thickness, width, length are showing here. And if you substitute, or if you fabricate a cantilever beam and to measure the stiffness, you will find out that the stiffness will be 1. This is the initial design. It seems everything is okay. Why bother to find out another design, right? Now we want to use Takeuchi method, try to find out another design to see if that another design will be better than this initial design in terms of quality. Here, we don't have time for the experiment, so we are using this equation to get the number of the stiffness, EPH power 3 over 4L power 3. And this is the inner array. We arrange everything here. This is the range for each design variables. And we select here L9 for our design, and we put it into this orthogonal array. And then we need to find out what is the K. If in the past we are using random sampling, now we want to use outer array. So how about the noise factor? Right now in the example or in the video, we only concern 3 noise: length, width, and height, thickness. So 3 noise, 2 level, L4 is good, so put in L4. This is L4. And again, level 1 of delta B stands for the low level of the noise. Delta B is minus and plus 0.03. So level 1 will be the lower bound, make it minus 0.3. Delta L, level 1, make it a lower bound, minus 0.12, etc. So by arrange these noise factors into this outer array, we will have the outer array sample. And how do we do the experiments? This is how we do the experiment. We have 2 orthogonal array, and often we will arrange this one in this way. We put the outer array to the top and put it on top. Therefore, this simple 1, 2, 3, 4 will stand for this 4 combination of the noise factors. So it will be easier to put it in one table. So this is the inner array. That is outer array. And for the outer array, this is the noise factors. And for each outer array, this stands for 1 sample. So under the influence of this outer array, we get a sample output. Same thing for Y2, Y3, Y4. Under different influence of the noise factor, then we can calculate the mean, standard deviation, and average. Mean, standard deviation, and SN ratio. And this is the example in the video tape. After we get that, we'll have the SN ratio, and the rest of the result will be pretty much the same. And these samples will show you how these control factors are influenced by these noise factors. I have done that in the quiz, but again, here we put out, this is design number 1, and when it is under the influence of these 4 treatment, which means the four combination of the noise factors. So in the first inference, there will be that. So you put this number into the design, you will find out under this inference, the sample, the actual number of the control variable will become this one. Okay, and from this number, we can fabricate a cantilever beam and calculate what will be the stiffness. And in this case, we just substitute this number into the equation. Continue to do the same thing for the second sample and the third sample, the fourth sample. We can get all the sample output under the influence of this different combination of noise factors. Therefore, for each design, we will have 4 samples for K, average, standard deviation. Then we can get the SN ratio. Doing the same thing on the second, this is second design, first design, right? So for each design, we'll have 4 samples. So there will be design 1, design 2, etc. So in order to make it easier, we put it in this way, this orthogonal array arrangement. So we have the SN ratio. Then the result after that will be very similar to what we have done before. We need to find out what is the SN effect plot, actually from the response table, find out the effect plot, then find out what is the best combination. All right, what is the best combination? Let's work on this example, but a little bit different. We will work on the 4 noise factors. We add the noise for the Young's modules in and try to find out what will happen. And this will be the homework we are going to work on during the classroom. This problem is similar to the one showing in the lecture notes and also in the videotape, but I have the number 4 noise factors. Number 4 noise factors. So here, this is a problem. Cantilever beam, we want to design the cantilever beam in such a way that the K will be equal to 1. And there will be 4 noise factors in this way, right? Okay, sorry. This is the control factors, the range of the control factors. And I already put it in 3 level, right? Put it in 3 level. Right, follow me, right? And the noise factor now will have 4 noise factors, as I mentioned in the PPT. We'll repeat the exercise, but using 4 noise factors. 4 noise factors. Well, what would be the difference between this example and the videotape example? Well, in the videotape example, we will have 3 noise factors. Each noise factors are set at 2 levels. And we need to select an orthogonal array for 3 2-level noise factors. In the lecture note, we select L4. But now we will have 4 noise factors. Can we still use L4? No. L4 can only good for 3 factors, right? If you look at the orthogonal array table. Then how can we do? We can only go up to L8. In this case, L8 have 7 columns, which is good for 4 noise factors. So we use L8. We use L8, right? By using L8, then we need to assign our factors into this orthogonal array. In this case, let me double check. In this case, assume we are assigning data B, data L, data H, data E to the first 4 columns to L8. Then, how can we do? How can we come up this cross array experiment? So this homework will ask you to do the similar process, but using 4 noise factors. First, this is a process. Basically, this process is it is actually a reminder to ask you what will be the procedure to finish this process. Okay, I need to finish this exercise. So let's go to the exercise. From the exercise, you will have, I believe this is a file you get from the videotape, right? But it is only good for 3 noise. Right now, we will have 4 noise. Delta B, delta L. What will be the order? Let me check. Let me using this order. B, L, H. Okay, B, L, H, E. All right, using this order. I'm sorry. 1, 1, 2, 2, 1, 2, 1, 2. Sorry, let me check. So we will need another array here. And this is supposed to be delta E, Young's modulus, right? Now we need to find out what it will be the orthogonal array we need. We know that we need to use L8, right? L8. Then let's look at the L8. Assume by choosing the first 4 columns, then we know that we will have 8 samples. So we need to put this orthogonal array into our experiment by transpose, move it to the top. Then you will know you need to have now 8 columns stands for 8 samples. 4 rows stands for 4 noise. Now we have 4 noise, but sample is not enough, not L4. We need to use L8. So we need to have more columns. Well, the easiest way is to copy, right? Copy. And can I just pass it? Pass it. But when you pass it, you move it to the right. All right? And continue. We have all we need. Right? Then we can number that 5, 6, 7, 8. Then we will have 8 samples. We need to kind of reform or try to modify the example I give you before, and to make this experiment can accommodate L9 and L8. It was L9 and L4. But now we need to make it L9, L8. Also, this level of noise are not enough. We need to, okay, let's move it up here a little bit. Okay, we need to make it another noise, which is delta E. Copy, pass it, but it should be delta E. All right, now we have 4 noise. This is number 4 noise, delta E. The first level, let's make it small number, minus 5%. And here will be plus 5%. So this is the noise factor, outer array, and also the level selection for the noise. You need to find how to arrange the enclosed array is very important. You need to learn how to do that by yourself. Otherwise, you can only use the table I gave you. Right now, I only modify the outer array. In the future, in case L9 is not good enough, in case L9 here is not good enough, such as if you have more factors. Right now, we have 4 factors. If you have 5 factors, then L9 will not be good enough. Then you might need to choose, for instance, L18. Then you will have L18 here, right? And by understand how many noise factors you have, what will be the label, you need to select an outer array to accommodate these noise factors. In this case, will be L8. And this is how you come up L8. This is the level 1122, 111222. Okay, let's make it number here first. 1, then this is 1, 1, 1, 1, 2, 2, 2, 2. All right, and this will be 1, 2, 1, 2, 1, 2. Okay, easy. 1, 2, 1, 2, 1, 2, 1, 2. All right. This is the outer array. First 4 columns of L8. And we are from this L8, and we assign these 4 noise to the first 4 columns. Therefore, we will have the L8 outer array. Would it be okay? 好，那个家人帮我看一看，是不是大家目前都还好哈？ Right, once you have find out what will be this L8, next one is you need to substitute a number into this experiment, outer array experiment. B, level 1 will be -1. So here, this will be -1, -1, and this will be -2, plus 0.03. All right. Sorry. Okay, then you can finish the outer array experiment. And then change the color back to black. Let's make it blue, right? Centered. And then make it red. Same. Okay, remember I didn't copy the number over because in this in this level here, instead of typing 0.003, I using equal to minus the number here. So you cannot copy this over directly. You can only copy the number. Otherwise, when you copy this into the next row, you will copy the equation, which means that you become plus minus, like what I did before. Okay, that's the reason why I copy 0.03 here. It becomes minus 0.03 because I was copying the equation. And the equation say the number will be the negative for the last cell. Okay? So be careful here. Right? This is not the number, but the equation. Right? So I finished all this outer array. Any problem? Any problem? Let's take a 5 minutes break, okay? Let's take a 5 minutes break and come back at 11:10. Then we can continue how to finish that. Actually, it is very simple. If you can finish that, I believe you can finish that by yourself. Okay, let's continue. Any questions for this arrangement of cross array experiment? Inner array and outer array. All right. Then we can start to experiment. But as I mentioned before, we don't have time for experiments. So we are using this equation. Okay, this is SN ratio. We're using this equation. Where's the equation? Right here. Let me copy the equation over. We are using this equation as a data generator, right? Using this equation. Remember here, it might be a better idea that I put a quote here. Otherwise, you might be confused, right? So now we need to use the equation. Actually, it is very straightforward. The only trick is that we'll try to copy our equation over without typing all these long equations. So there will be some trick. So this will be EBH. So let's find out what is E. The original equation, still need to make it a little bit smaller. The original equation will be equal to E is here. E multiply B multiply H to the power of 3. Okay, I follow the equation here. E B H to the power of 3 divided by 4 times of L to the power of 3 divided by, quote, 4 times L to the power of 3. This is the original equation here, okay? This is the original equation. And this original equation was EPH, this one. But when we do sampling, we do outer array sample. In first sample, in this first sample, you're under the influence of these noise factors. Therefore, this value will be different from the original value. For the original value, okay, sorry, I haven't finished that yet. I need to put 1 to be 4, 5.3, and 6.6. I will do that later, okay? The value will be contaminated or will be influenced by this noise, which means that for original Young's modulus, let me finish that first. Oops, sorry, finish that first. You need to fill out this number, and I believe you can do that. Level 1, B, level 1 will be 4. Level 1 for level 2 will be 5.3. I think should be very straightforward. Okay, this is how you put it into that, and then you can finish that. 3 will be 6.6. Okay, once you substitute level 1, 2, 3 into this design, you will get the experiment design like me. Okay. Okay. Let's come back to the first equation. Any problems? So I forgot to done that. I believe you should have know what to do. So finish the control factors and the noise factor arrangement. And let's come back to the equation. It was, again, E, B, H to the power 3 divided by 4 times of L to the power 3. The original equation is like this one. But we need to do, when the first sample is assumed, you are under the influence of these noise factors. Therefore, the number will be changed. How will they change? The E here will not be a simple E. E need to be minus 5%. Remember, not minus 5%, but need to be multiplied by 0.95. Okay, or this number should be A should multiply by, because it's minus 5%. So it will be 1 plus the arrow. Okay, it was 100%, but now it will minus 5%. Minus 5%. Okay, but I didn't type minus 5%. I just plus the inference of the noise on the control factors. So 1 plus minus 5% will become 0.95, 95%. Multiplied by this value will be the exact value when this design under the inference in the sample number 1. And about B. B is more straightforward. It was A12, this number. But now you're under the influence of this arrow. So the actual value need to plus the arrow. In this case, I just plus arrow, since this is a tolerance range. But for Young's modulus, it is different. The arrow is represented as a percentage of the value. So that's the reason why these two arrows need to be calculated differently. Same thing for H. H, the actual value need to consider the noise, which will plus the noise, which is this one. Same thing, divided by 4L. L has to consider the noise, which is this one. Okay, any question? The equation is right here. E, B, H to the power 3 divided by 4L to the power 3. But now each value will be influenced by the noise factors. Either they are tolerance, lower bound, upper bound. So I just plus the arrow. If the arrow is minus, then you'll be lower bound. If the arrow is plus, then you represent the upper bound. And remind you again, for the Young's modulus, if the arrow is represented by the percentage. So the actual value should be value multiplied by the percentage. So when it is minus 5%, 1 plus minus 5% will become 95%. So which means that the value, actual value will be only 95% of the nominal value. Let's do it again. Actually, I don't want to do it again, okay? In the videotape, I do that again. So the value will be 1.152. If you get 1.152, then you're on the right track. How about the second one? The second one. In the second sample, it is still these factors, but the noise will become this column. So we can type in the equation again. But I want to say, teach you a trick. Can I just copy the equation over? Well, it seems I cannot, because when I copy this over, the number becomes 0. Let's see what went wrong. When I copy the equation to the next column, remember because it's an equation, it is a reference, all the columns will automatically plus 1 will become the next column. For the arrow, it is correct, since we want this column of arrow to apply to this design. But for the design variable, control variable, it's supposed to be fixed at BHLE. But when you copy this one to the next, it will automatically shift to the next column. Then it messes up, incorrect. So what can we do? We want to make sure that the control factors, remember, control factors, the columns of the control factor will stay at A, B, C, D. So how can we do that? Go to this equation again. What is the control factor? This is a control factor, D12, right? D12. And we want this control factor, the column will stay the same. So we add a dollar sign to the column. Make sure when we copy the equation, column D will stay there. The column number will not change. Next, this one. This is another control factor, A12. This is B, right? B. And has to be in the column A. So A needs to be fixed. How can I fix it? We can type dollar sign in here, or you can just press function for F4. F4, right? F4. Okay, you'll put dollar sign in both again, in row number again, column number. That's it. Do the same thing. H. Press 4. Make sure that the column will have a dollar sign divided by 4L. This is the noise. This is the control factor, C12. Press F4. Make sure that the dollar sign will fix at C. Then we fix half the problem. What do I say? Half the problem. Because when I copy the equation to the next, it is correct. Why it is correct? Let me click the number again. Well, the equation is correct, right? When you look at the equation here, control factor E, well, stay the same. Stay here. E, right? B, the same. All the control factor will stay here. And the noise factor, when I copy over, the noise factors automatically shift to the next column. That's what we need. Okay. But why I say I only solve half the problem? Because again, if you copy the equation downward, let's try this one. If I copy the equation downward, what happens? Let's click on this cell and click to see what is the equation. The equation looks okay, but the control factor looks okay. But the noise factor, when I copy downward, the reference row number will automatically increase by 1, which means that the row number was 7 to 10, but now it becomes 8 to 11 downward. That is incorrect, which means that we need to fix the noise factor, the row number of the noise factor, to be fixed at 7, 8, 9, 10. How can I fix the noise factor row number? Just like what we did before, let's go back, delete the equation. Let's go back to the original equation again. Where was the noise factor? This, okay? Here, F4, noise factor, F10, F8, F9, right? These are the noise factor. But the row number 7, 8, 9, 10 should be fixed. So we come to the equation here, press F4 again, fix the row number. Here, F4, fix the row number. So the trick is fix the column for the control factors. So because the control factor will stay in A, B, C, D column. Fix the row number of the noise factor because the noise factor will stay at row 7, 8, 9, 10. So you can see the equation here. Some fixing column, some fixing row. Once we have done that, the sample of the first one is remain the same, but when we copy the equation to the next 8 columns, it will give us the right number. Okay, let's click here, try to see if they are correct. See, you can see, let's make it a little bit smaller. Click here, you can see that all the equations are correctly, right? This is the control factors. This is the noise factor when we do the number 8 sample. Let's try any of them. How about number 6? Click. Well, it is correct. After you finish this one, how about the rest? You can just copy the equation all the way down, and you can finish the experiment like that, a simple snap. Remember, this is only a classroom example. So we can use this equation using this trick to get a number very quickly. But in fact, in the real world, you need to do experiment for each sample. So that's the reason why we want to reduce the number of samples by using outer array and inner array. However, we still maintain the required precision. Once you finish that, everything else is the same. Now you need to find out what is the average, mean. The average will be the output of the L8, 8 sample. Standard deviation, the standard deviation will be this 8 sample. How about the SN ratio? Will be equal to, I put the equation here, and okay, it's a little too bad that the standard deviation is blocked by the equation. Okay, I cannot select this cell, but you can type the cell directly. It is O12. So you can divide it by O12. Okay, square. This is SN ratio for the sample, for the first design. For the rest, we can just copy the equation downward directly, and let's double check a little bit. Okay, the equation is right, and mean is right. You will automate, because you are copying downward, so you automatically increase the row number by 1. That's what we need. We can get all the output, SN output for all the 9 design. Once you get so the only difference is how to come up this crossed array experiment. How to consider the noise factors influence on your design and do the sample. After that, when you get the SN ratio, the rest are the same, because the next step, you need to do the response table and effect plot for all the control factors. I'll leave that to you. Yep. And the result will look like that. This will be your response table. And you need to do 2 response tables. The first one is according to the average output. The second one is according to the SN ratio. So you have 2 response tables. And from that response table, you will have 2 effect plot. I'll let you finish that. I think you should be able to finish that, because this is exactly the same like what we did on the like I played example. Okay, the response table for the average and SN ratio will be exactly the same. So like this one, this is the SN ratio. For B1, I select B, and the next one is 1, okay, and corresponding output is here, SN ratio, and we'll calculate the average. If you have any questions, let me know. Why we need the 2 effect plot? Because we need to classify these control factors into that 4 category in order to find out which one will be good for the scaling factors. Okay, if you have any questions, raise your hand. Otherwise, you should be able to find out the effect plot for mean and the effect plot for the SN ratio. Okay, I would suggest you to finish this Excel first. Don't worry about the Word file yet. Okay, but if you finish this already, then you can type in the Word file. Here, the exercise, first one, he wants you to come up the K and SN, just like what we did, right? This is how you get your design for experiment right here. So this is your design for experiment. So once you finish that, you can copy the whole thing over to the Word. I'll teach you a trick here. When you copy your table, if you just simply using Control V, it will be huge, too big. Then when you try to reduce it, the number will mess up. So here I will suggest you to using copy picture, right? Using the picture. Because when it is a picture, the arrangement, the proportion will remain the same. Right? Using picture. Although it is small, but that's okay. That's okay. You can, in case you can want increase a little bit, so you can increase your table a little bit, or okay, you can change the boundary and make it a little bit bigger. But we will understand why this table is, because this table is big. That is the reason why in the lecture notes or in the videotape, I use L4. I only consider 3 noise, because then we can use L4 for the outer array. The whole table will be not that wide, not that big. But for this real exercise, we'll ask you to choose L8. Consider 4 noise factors. Any questions? And the next step is what I ask you to do. You want to calculate the response table. Okay, calculate the response table. Next, you want you to draw the effect plot. Effect plot, right? So this is very standard. So that's what I mean, that you can work on the table, Excel table first. Once you finish that, then you can draw the effect plot. Okay, this is an effect plot. Then you can modify a little bit, such as the title. Make sure this is the effect plot. Make it happy, right? You always type the title. This effect plot of mean, right? Then you need to fix the continuing problem. So click again, right click, select the no, right? Then click this one again, double click, Control Y to make it repeat the last motion. Click, Control Y. Then you can finish this effect plot for the mean. Do the same thing for the SN ratio. Let me know if you have any questions. Let's start to find out what will be the optimum design. First, this is the initial design. I already type it here. This initial design is the same as the problem here. We show you this is the initial design. And what will be the output of the initial design? Let's go back here. This is the number of the initial design. What will be the output? We can, because this is initial design, is not one of the L9. Therefore, we have to do the same sampling. We want to do the same sampling and find out what is the corresponding mean, standard deviation, and average. So we copy the equation and pass it over. I just pass the equation. So I can find out what will be the L8 sample for the initial design. And the average of the initial design is pretty good. 1.0022, very close to the required stiffness, k equal to 1. Standard deviation and the SN ratio will be 22.75. If you look at the SN ratio, you'll find out that this number is not very good. Not bad, but not very good. Because looking at the L9 example, you can find out some of the samples are better than 22.75. That's the reason why we want to use this Takeuchi method to find out a better design. A better design in one way, they have to have the same performance, which is k equal to 1, but the standard deviation or the SN ratio will be bigger. How can we do that? First, the first step, like I play example, is to find out the combination of the maximum SN.